water and you hear something happening, you hear a funny sound, that's what you hear when you hear auroral scattering in your headphones. Tropoducting, well, that one's complex, we'll get to that. Sporadic E's have to do with the E layer and just a long bounce. Ground wave and sky wave. Well, ground wave is what AM radio uses only, unless some of the big stations at night do all of a sudden start spreading out over the whole country. But normally they just use ground wave and they don't have any skip off the ionosphere. They don't do anything except send straight out. And you only have a very short radius of reception.
6 meters, where's 6 meters called?
6 meters is between VHF and HF. And
but sometimes it goes long, and which arenas does it fall in?
You're going to get a lot of tropoducting on 6 meters. So when we get to that, ask the question again, because you're going to see 6 meters fits in that. Sometimes it does HF stuff, sometimes it does VHF stuff, and sometimes it does only 6 meter stuff. Like Gray Line is really 6 meters, but it's really fun at CW. Here we have our ionized layer in the atmosphere. The sun comes along and it's sending out some UV rays. It comes and it hits oxygen and it splits off. So you have O2, now it becomes O1 and O1. Well, that now hooks up with some other O2 and you've got O3, which is ozone. Then since it's unstable, it breaks off and it forms another O1 and O2. And depending upon how active the UV radiation coming in is, you have all sorts of ionization happening in the ionosphere, making ozone, eating ozone. So ozone is something that is in steady state if there's high radiation coming in. During the nighttime hours, ozone tends to drop off in concentration. During the day, it tends to increase in concentration. That's only one of the ions. There's a lot of other ions.
Basically, if there's a high radiation, then the ozone breakdown combinations are often enough and steady enough that it sort of looks like solid steady state.
Very steady state, yes. Except there's times when it looks like it has ripples in it. And people will tell you that reception is reciprocal, meaning if I can hear you, you can hear me. No, that ain't necessarily so. Because the ionosphere can be kinked in such a way that I'm shooting right over you, but it's kinked in such a way that I'm hearing you perfectly. So I'm giving you an S9 and you're going, I can just barely make out a call sign. Thanks for the QSO, I gotta go, I can't hear you. And then 15 seconds later, it can be perfect again. It can shut off, open up for just a few seconds, and then it can shut off just as rapidly. Because what happens is clouds can come through this ionosphere and change the angle of incidence. So what was shooting straight up into space, all of a sudden gets bent. If you just change the angle of your antenna or change the takeoff angle of your antenna, all of a sudden you're now getting 1,200 miles away, whereas you were getting no one before. You change the angle a little bit more, you bring it in closer and closer. There's all sorts of things you can do with phasing to change the takeoff angle, but basically we're talking about the way the ionosphere changes on a minute-by-minute basis. I have a daily sked with a friend of mine, he used to be in Oklahoma, now he's in Alabama, and during the equinoxes we always have a problem making contact. So we normally set our time, our sked time off by half an hour because just that half an hour means the sun's been up longer here than half an hour earlier, and all of a sudden the ionosphere is good enough to support our contact. Whereas early on, if we try to make contact in the first minute or 10 minutes of our hour, we can't contact each other at all. He's running a Yagi and I'm running an inverted V, which makes a little bit of difference, but basically it's the ionosphere. Other times the QSB is very, very strong and regular. It's like the ionosphere has waves in it, like waves in the ocean. And it's very, very, you can hear them. All of a sudden it gets really loud and then it's really faint, in and out, in and out. One equation you should remember, because this one allows you to figure out your antenna lengths. C equals lambda F. Lambda is the wavelength of the frequency of you're on. So if you have a half-wave dipole, you take half of the wavelength. So for a 40-meter antenna, you have approximately 20 meters, which is approximately 60 feet. So that would be the length of your dipole. Trouble is, you also need to figure in your, what is that speed called of your coax?
Velocity.
The velocity factor. I've heard some people say the velocity factor makes a difference. All you really need, you need to know it because that tells you how fast. All you're looking at is the speed of light in a medium. 300 million meters per second, is really in free space. If you're sending something through wire, or you're sending light through water, or you're sending light through something else, you're going to get a different speed. And that's why these work, because the index of refraction is changing, so it bends the light so I can actually see you folks. Same thing's happening with the ionosphere. The index of refraction is changing, so it's changing the speed of light in a medium. So it's bending it because you have that difference. F is in hertz, by the way, and F is in meters. But that one is always good to know. And if you just do 300 times 10 to the 6th, so if you do 300 and everything's in megahertz, you can do 300 divided by your frequency in megahertz, and that's fine. And in VHF, UHF, everything's in megahertz anyway, so that's a good one to remember. But you need to know the velocity factor. The problem with 2 meters, 70 centimeters, 220, 1296 is they tend to cut right through the ionosphere and keep on going. But if you can aim your antenna's takeoff angle low enough, you can use a grazing angle through the ionosphere and you can do some amazing stuff. Like we can work Hawaii on 2 meters with 5 watts or less. Not a problem. I wouldn't advise using FM, single sideband, or CW on 2 meters. And you should be able to work. You probably will not be able to do that to Alaska. It tends to be over water and over warm water because the index of refraction is such that it will hold your beam down low enough. But you're going to have to adjust your antenna to try to get your takeoff angle just so you get the grazing angle. You can do it.
So how many, is this like a multi-element Yagi 2-meter antenna to do it? So
Yeah, I would go with that, like a 12-element Yagi. Oh, in the next lecture, I'm going to tell you the history of that. Mr. Yagi did not invent the Yagi antenna. Mr. Uda did. Mr. Yagi was the guy who wrote the paper in English that got published about 3 years later, and that's why we call it that. And the funny thing was, during World War II, the British knew more about the Yagi antenna than the Japanese did. The Japanese captured a British aircraft and figured, what are these antennas? The Navy knew what they were, but the Japanese Air Force did not know because there was such infighting between the Air Force and the Navy that this information had not been spread all over the Japanese armed forces. So they had to find out from the British something that had been invented by them. Well, we had to find out from the Germans something that got invented by us. It happens to be the V2.
I know they kept saying ask Goddard.
Yeah, they did.
When they were being asked questions in interrogation. Ask Goddard.
Yeah, Oberth didn't invent it, he just adapted it. So, if you increase the frequency, you're going to tend to cut right through these various layers of the ionosphere. As you lower the frequency down, and especially right near 6 meters, all of a sudden this is going to start to take place. The trouble is, right now we're at solar minimum, and the ionosphere is not really intense. You have to concentrate on any solar wind, any coronal mass ejection, any little thing that happens changes how well you're going to get through right now.